Welcome back. So for the final part of our series, we're going to look at material science through a really crucial lens, the patent office. We've spent all this time exploring how materials get made and what they can do. But today we're asking a totally different question. Where exactly is the line between discovering a material and actually inventing one? Let's dive in. This is the fundamental question that technical experts and patent examiners have to wrestle with every single day. If you stumble upon a new mineral out in the wild, well, that's a discovery. But what if you create a brand new material in a lab? Is that automatically an invention? The answer, it turns out, is surprisingly complex, and it really all comes down to defining what a real technical contribution even is.
Okay, so take a look at this, because this slide presents a fascinating little puzzle. All three of these discs are made of the exact same chemical, aluminum oxide. But obviously one is totally transparent, one's kind of translucent, and the other one is opaque. So if the chemical formula is identical, what's different? And more importantly, where is the invention here? It's clearly not just the chemical itself. It has to be in the engineering that managed to create these totally different properties.
To figure this out, we're going to put on a new hat and think like a technical expert at a patent office. First, we'll talk about what it takes to go beyond just discovering something. Then, we'll look at the core questions an examiner is always asking. After that, we'll see why unexpected effects are the absolute key to innovation, and just as important, how you prove it. And finally, we'll see how this all gets packaged up into what you could call the engineering of an invention.
All right, so let's start by building a framework for how to think about this. To separate a simple discovery from a true invention, we have to get our heads around this idea that, in material science, a patent isn't just about identifying some new substance. It's about demonstrating a new cause and effect relationship that you, the inventor, have engineered. It's not just about the what, it's all about the how and the why.
And at the very heart of all of this is something called the materials paradigm. It's actually a pretty simple but incredibly powerful chain of logic. It goes like this. The way you process a material determines its internal structure. That structure is what gives it its properties, things like strength, or like in our earlier example, transparency. And finally, those properties are what determine its ultimate performance when you try to use it for something. This is basically the blueprint for all of material science.
And this diagram, this illustrates the crucial point perfectly. A patentable invention isn't hiding in just one of these boxes. It's not just a new process or a new structure all by itself. No way. The real invention is the new, non-obvious link that you forge between them. It means you figured out a way to process something that created a structure with properties nobody thought was possible, leading to this incredible new performance. That entire story, that is the invention.
Okay, now let's try to step into the mind of a patent examiner for a minute. And don't worry, we're not going to get bogged down in legal jargon. Instead, we're just focusing on the fundamental technical questions they ask to figure out if a genuine innovation has actually happened. You should think of them less like a lawyer and more like a technical auditor, just checking the work.
So, all across the world, examiners basically use three main tests. First is novelty. Is it actually new? Then there's industrial application. Is it useful for something? Can you make it? Those two are usually the easy part. The real challenge, the place where most materials patents are either won or lost, is that third one, the inventive step, or what a lot of people call non-obviousness. In other words, was this an unexpected leap forward, or was it just the next logical step that any expert in the field could have taken?
So the big question is, how do you prove that what you did was a non-obvious leap? Well, this is where we get to the very core of what a technical contribution is. It all, and I mean all, hinges on demonstrating an unexpected technical effect. You have to be able to show that your material does something surprising, something that the existing knowledge base, what examiners call the prior art, would have never predicted.
This quote about nanotechnology is just a perfect example. You can't just take a material everyone already knows about, shrink it down into nanoparticles, and call it an invention. Why not? Because that's just changing a parameter, a dial on a machine. To get a patent, you have to prove that making it smaller created some new, unexpected technical advantage. Maybe it suddenly becomes a much better catalyst, or it gains some weird optical property. The effect is the invention, not the size.
And this table just lays it all out so clearly. On the right, you've got what's basically mere description. Using methods that are already out there or talking about an effect without really anchoring it to a specific structure.
But on the left, that's where you see true innovation, showing non-obvious changes that lead to brand new effects, providing hard evidence that it's a reproducible phenomenon, and clearly linking the features of your material back to why it works.
Now, claiming you have some amazing, unexpected effect is one thing, but as any good engineer or scientist knows, a claim without proof is, well, it's pretty much worthless. Your technical story has to be verifiable. An examiner needs to see cold, hard evidence that what you're claiming is real, and not just some lucky accident you had in the lab one afternoon.
And the absolute gold standard for that proof is reproducibility. This is a concept that comes straight from the heart of the scientific method. It just means that somebody else, another skilled person in the field, can pick up your patent, follow your instructions, and get the exact same result. It is the ultimate proof that your effect is a real, controllable phenomenon, not just a one-off fluke. And as this quote makes crystal clear, this isn't just some nice-to-have. Reproducibility is the strongest evidence you can possibly provide that you've moved beyond simply describing something you saw once and into the realm of a genuine technical advancement. It's the absolute bedrock of a strong patent application in materials science.
So let's bring this all together now. You've found a new material, you've identified that non-obvious link, you've demonstrated an unexpected effect, and you've proven it's reproducible. The final step is packaging this all up into a coherent technical story, the engineering of the invention itself. The Japanese Patent Office actually provides a fantastic hierarchy for how to do this. The best, the most robust way to define your invention is by its structure, its chemical composition, its crystal arrangement, things that are concrete and measurable. If that's for some reason impossible, you can try to define it by its unique function, and then only as a last resort do you define it simply by the process you use to make it. You can see there's a clear preference for defining the cause of the effect, not just the effect itself.
So here it is, the crucial takeaway. The invention is not the material. The invention wasn't the aluminum oxide. The invention was the clever engineering that turned it from an opaque powder into a transparent window. It's that new, non-obvious, and reproducible cause and effect relationship that you discovered, you controlled, and you can now explain to the world.
And let's bring it right back to our paradigm here. What a patent truly protects is not any single one of these boxes. It protects the technical story, the intellectual property that connects these boxes together. It protects the recipe, the logic, the new piece of science that you've established and proven, which allows you to predictably create a material with properties and performance that no one else could before. So as we close out this series, I want to leave you with this question. The next time you look at the super strong glass on your phone, or you think about the lightweight alloy in an airplane wing, or even the high-performance fabric in your jacket, remember, they aren't just materials. They are the end result of an engineered invention. So ask yourself, what invisible technical story, what non-obvious link between processing, structure, and properties is hidden in the materials all around you?